Okay. Hello, guys. Thanks for joining in. Love to see some familiar faces here already, and I hope for the rest that I can show you something cool. I'm Ruben, and I'm going to talk you through Pixi today. It's a cross-platform package management tool, and it's really cool for modern C++, and I'm going to show you that today. So first, I'm not alone in this. We're a small startup in Europe. We've currently been working on package management for 3 years, but we're coming out of an ecosystem. Prior to that, our CEO built Mamba, if you're familiar with the Conda ecosystem. We're solving our own problems. So we're all from game development, robotics, data science, and all these kinds of different ecosystems where package management was still always a pretty big problem that we needed to solve. Thus, this company is solely based around the idea of helping package management be easier for everyone to use. So first off, this talk is not about a C++ package manager, it's a talk about a package manager. We're not a Python, a Rust, or any type of language. It's something different. So why should I still care about this? This is a C++ conference. Well, C++, like any other language, can benefit from the generic package management. So you're probably familiar with Homebrew, with apt-get, with winget, or any other system language, system package manager. And Pixi can do the same thing. So you have the ability to have any type of package, any type of language on basically any type of OS. So we support Windows, Mac, and Linux directly out of the box. You can do it with binary and source dependencies, and I will show you some examples later. And one of the biggest focus points of Pixi is reproducibility. So the ability to get your environment set up and then later on do it again, which might sound pretty easy, but I think all of us have had a situation where it was not that easy to get it set up again. And Pixi makes that really easy. So to give it some credit, we have already a lot of users, but one of which I think is really cool, and especially for the C++ community, is FreeCAD. FreeCAD is an open source C++ developed computer-aided design program. And as all of these open source tools these days, there is the description on how to compile it on Linux, how to compile it on Windows, how to compile it on Mac. But there's also now a description on how to do it with Pixi, because as soon as you do it with Pixi, there's just a few commands left that you need to run, which are all cross-platform, and you don't really need to take your users through a huge README to get it done. Basically, it documents itself, and the README just contains how do I get Pixi, which is a one-liner for your machine, and then maybe 3 or 4 commands to get your full system set up, and probably your build run as well. So before I go into more details on like the Workspace workflow and all of the cool stuff that you can do for your C++ projects, Pixi also ships a Pixi Global, which is a tool to install tools on your machine. So in this small example, it shows you that it can install Git, it can install Z, the editor, it can install nvim, pcpackage, or Conan. If you want to use different types of package management within your system, you can still use Pixi to get those installed on your machine. So it will give you an isolated environment with these tools installed. So not like with apt, you have only one version that you can get, or you need to play with repositories. It is a normal versioned package management system, and it will put it in its own isolated environment. So if you have a dependency in the Git environment that you need to update, you can do that. It will not touch the environments of any of the other packages that you're installing, making it really stable on your machine. It also comes with shortcuts and auto-completion, which means that it can also have like menu items. For instance, in the Z example, we have the shortcut Z that is installed in your menu, or in your start menu, or in like the desktop file on Linux, or for every system it has its own way of doing that. But Pixi simplifies that into one command that you can run on all of these platforms. And especially, it doesn't need any activation. So if you're familiar with the Conda ecosystem, you often have to activate these environments. These will be installed without the requirement of an activation. So they will, you will just have them always active in your CLI. So you can just type git without an activation first. Mainly meant for tools, so don't try to get complete workspaces installed globally. I don't think that's the best idea, but it could be an option for you. So we're going directly into a little demo. And this is a Pixi Workspace demo. What you see here is the Pixi manifest. I will tell you a little bit more about that later, but the idea is that you have one file that describes what does my environment look like, what does where do I get my packages from. So in this case, we define that we get the packages from Conda-forge. By the way, is this readable for you? I think I can grow it one tiny bit. You define which platforms your project should run on. So in this case, we want it to run on all the ecosystems like Mac, Linux, and Windows, which means that Pixi will always check, hey, all the dependencies that you depend on, are they installable on these machines? So for instance, some of the tools, some of the packages are not available on Windows, and Pixi will tell you that before you try to ship it to your colleagues that are actually on Windows, and that might require that dependency. In this case, you can run Pixi add, and just like your normal package manager workflow, we call it add, some call it install. That's the same thing, but it will add that line also to this manifest. So if you then expect this state to change, this is always done through this manifest, and you will get a declarative experience instead of your system holds a certain state. Getting into that state might have become a long list of different commands to get you there. We always work from this manifest. So the CLI will just update that, and from that point on, Pixi will do the rest of the workflow. And I also added Python here just because a lot of C++ developers use Python. Pixi can install both of these things at the same time. So again, not just a tool for C development. I will quickly show you what that looks like. So if you, for instance, want to update and resolve the whole environment, you can just run Pixi update, and it will fetch repo data. Unfortunately, that's going to take a little bit of time due to the internet speed here, but that was a solve for all the platforms at the same time. If you're coming from the Conda ecosystem, that might have taken a few seconds. In this case, it was just the internet checkout that we need to do, but the rest is like instant, and we really optimized this workflow for everyone. Then there's another thing you might have already seen. This is called tasks. So in Pixi, we have a task shell that we ship with the binary itself. So these tasks are cross-platform. So if you start using environment variables or something like that, you define them like you would do with Bash. And then that would also work on Windows. It would also work on Mac. The cool thing about this, we can do a little bit more than just running a command. So it's not just an alias. You can also get these graphs of tasks that you define. So in this simple example, we're running some CMake. You have a configure task, a build task, and a test task, but we can depend on each other. So of course, build depends on configure, and test depends on build. And in this case, it will automatically execute them in the right order. So I'll quickly show that that works. Pixi run test. First, the configure will be run. Then the build. Pixi will also tell you what it ran in between with these little headers. And it installed this little example. So I have some boost. I have a CMake list to get that set up. A cool thing that Pixi allows you is you're not locked in. So you can still use your normal workflow. You can still use your favorite way of dealing with CMake. If you're doing CMake, if you're doing Python, all of that works. We have this extra file that you can add, and that takes care of all of the package management issues that you might get to. So we don't try to lock you into a different way of working. We work with the normal ways. And for instance, you could, in theory, just use Conan within this environment and let Pixi set up the basics and let Conan or VC package or Nix or whatever continue from that point on. One thing I want to quickly show you as well. This is the log file. Looks like a really long list, but what it does, it gives you which packages I specifically installed from which channel, which version, and it goes a little bit deeper than just one file name. It also says the SHA hash and also the license that it comes with. So this is a file that's very human readable, but you can do some checking on it. So it gives you some metadata that you can use. And this actually makes it reproducible because now we've solved it. It is in the log file. If we add this to Git, this will be easy to reproduce for anyone else. Then one very important thing, if you want to get it tested, you normally build some CI. So if you're familiar with GitHub Actions, you need to define this workflow file. You normally would say, okay, I need to run on all these machines, but per machine you have a different way of installing. This is something that you have to get close to what you're doing locally. This will never be exactly the same. So a lot of people are trying to use Docker for these kind of solutions to get a little bit of a similar workflow. A little example, what does this look like if you do use Pixi? In the case that you use Pixi, you again just define which platforms you want to run on, and basically only have this extra line to say, set up Pixi, install it, and set up this environment for me. And from that point on, you have the same exact environment that you tested locally on your CI, and from that point on, you can run the tasks like you did locally. So there is almost no difference anymore between what you run in CI and what you run locally. That is the first demo. So let's get a little bit more detail on what that does. So what you saw is that we have this workspace. In my example, it was called CppCon, but in this case, it's workspace. And in workspace, we have a .pixi folder. And that .pixi folder contains the environment that we've installed. This is local to the project that you're installing. It will be linked from cache. So the files that are in here are not copied all over your machine. It will be, there is some logic to decide which is the most efficient way to link it into your environment, making sure that your cache is reused. But it looks like a normal, like Unix style environment. What this means is that you have to activate this environment. So when you install something with Pixi, it will not break your machine, but that is because it's not activated unless you really want to. So the files will just be there, and then to run it, you do Pixi run or Pixi shell. Pixi shell will activate the environment and give you a shell back. Pixi run will run that task shell that I talked about earlier and make sure that all the tasks that you want are executed in that environment. And this is always close to the Pixi toml file, and the Pixi will always put the Pixi log file next to that. So that's a basic workspace environment. So I already showed you tasks. What's really cool about tasks, it's very similar to makefile. You can also say, like, on the change of this file, we want to update this task. So if you do have a really long, really big graph of tasks that you need to run, Pixi will pick up, oh, I only need to run these tasks because these files have been changed. You can give aliases, you can give lots and lots of dependencies. We also have arguments that you can put in there and share them between these setups. So you really can make big pipelines of logic without needing to go outside and have another shell take care of this, or even go into like a Python script or something like that to do these sometimes simple tasks. I already showed you the log file, but I want to reiterate on why it's so important. We think it's really easy to always add this log file anyway. Like some people say, like, no, I make a library, so I don't want to add the log file. But the log file gives you the ability to decide when you want to update packages. And you can even go into CI and say, okay, always like not use the log file if you don't want that. But at least there is a way to get back to a situation that was working. So you now have the choice when you want to deal with these breakages. It also always logs all the platforms in one file. So this one file will allow it to work on all the platforms. You don't need to manage that yourself. It will make sure your CI is a little bit more deterministic. You can, of course, still make flaky tests, but at least your environments are exactly the same. You don't need to solve after it's already solved. Sometimes if you add some PyPI packages, for instance, you might actually need to set up some build environments to solve this. Pixi will not do that anymore because it already can read all of the information from the log file. And if you've added to Git, you can roll back. So you have the ability to check, okay, which changes were made. Let me check if an earlier version did actually work. And the GitHub actions again. It's a one-liner to get it set up, and you don't really have to think about setting up these actions anymore. What's the magic behind this? So we use Conda-forge as the main repository of packages. This is a repository that's community managed. There's over 7,000 community members that add different open source packages to that. But this is every type of package. So there's C packages in there, there's C++, Rust, Python, etc., etc. To give you an idea, this is, again, not a fair comparison, but to give you an idea, there's over 30,000 packages on there. And if you compare it to Conan or VC package, like we're not a small project anymore. There's a huge user base of users. But again, this is not the same type of packages, but to give you a little bit of context what 30,000 means, I think you can make sense of this. So Conda-forge has been built on the Conda ecosystem. This has been around for 13 years in the open source world. You might know it as the Python package manager, which it's not. I want to make that clear. It's not a Python package manager. It's a package manager that wanted to distribute compiled libraries for the Python ecosystem. And it became really good at doing stuff like C++ and stuff like Fortran because it was required for packages like NumPy and like SciPy. So that's where, from the ground up, it was built to deal with these kinds of workflows. And these days, it has gotten the name of the Python package manager, but that is not really fair anymore because it works really well for these other types of languages. Pixi itself, fully written in Rust, is also a Pixi package using all these Conda packages. So yeah, giving some credit to that workflow. So to strengthen the ability to develop these environments, what you previously saw was a workspace that has CMake installed, that has some compilers installed, that has some libraries installed, but it is still not a package. It's still a workspace. It's still an environment that you need to set up, and then after that you can do your own development. But what if you can have a package that is from source? And in the Conda ecosystem, you would normally use something called a recipe, which tells you how to build these items of packages into a Conda package. But we've introduced something new, which I will actually demo you, which is called source dependencies. So let me move to the source branch of this example. By the way, this example can be seen online. I can link it after the presentation. The Pixi TOML now looks a whole lot different. It still defines like where do I get my packages and which platforms do I support. We've added a preview to Pixi build because it's still in preview mode, this feature, but we are heavily building on top of it right now already. So in this example, I have added two dependencies, a C++ package and a Python package. You will not see the compiler here anymore. You will not see the CMake setup here anymore because that's now part of those packages. The tasks are now just the binaries that those packages will build for you. So let's take a short look at the packages themselves. So what you previously saw, the CMake list and the main.cpp, still the same. Only thing is that I added an actual install command to the CMake list, and then the Pixi TOML looks like this. So instead of the workspace, you will have a package definition, of course, a name and a version, and then you have a backend. And the backend is actually where all the magic happens. If you're already familiar with how the Python ecosystem uses build backends, we took a lot of inspiration of that. So what this will do, it will install the backend as a tool. In this case, the name of the backend is Pixi build CMake. It is an actual, it's its own binary, and it will be able to read this source and create a Conda package out of that. So if I run install now, because we have these path dependencies in here in the main root of the workspace, it will actually go in here and check out, okay, I have Pixi build CMake, let me download Pixi build CMake for you and run a build command on that, and then check out what information is getting out of that. And of course, we'll give you the name, we'll give you the version, and in the case of CMake, it will also make sure that it creates a build environment that has CMake, that has the compilers, that has everything like from a standardized workflow. This can be configured if you need something special, but just is that the basics will be set up for you like you would experience with like the build backends in the Python world. You can add more dependencies to it. So in this case, we're using Boost. So Boost is in this case a host dependency. You can think of it as a build dependency that you need to install for your target platform. And this will automatically give me libboost also as a run dependency of this package. That's some detail that I won't go too far in right now. But if I now do Pixi install on this package, you will see an actual build being run, actually of both the two packages, so also the Python package. I'll quickly show you that. The Python package is just a PyProject.toml. Pixi can also read PyProject.tomls. So we just added the tool.pixi in there, and the rest is exactly the same as your Pixi TOML manifest style. And instead of Pixi build CMake, we use Pixi build Python here, and that has the ability to read like the name and stuff like that from your PyProject.toml. And in the backend itself, it will use either UV or pip to do the actual building of this package. One thing I want you to note here is that, although it doesn't really make a lot of sense in this case, but you can actually have build dependencies from source. So if this CPP package was an actual library or something like that, Pixi will see that this is a build dependency or a host dependency in this case, and will make sure that it is built before the rest of the build dependencies. So you will get this graph of build setups that it needs to run. What it will do on your machine, it will create different build environments, basically the same logic as Conda build will do for you. So you have a host dependency, a build environment where your whole workspace is installed to build this package. This is similar again to how the PyPI ecosystem works. It will be an isolated build, and then it will install that build directly into your environment. And it will act like a normal package after that. You can have editable installs because there's a cool way of doing that. So we can actually build an editable Conda package from it and push that to your workflow. But the thing is that you actually can also have a fully released experience from your development workflow. Let me see if I can give you a little example. So for instance, now we want to rebuild this. And if you're experienced with Conda build, this will be really slow to rebuild. But if I just change this to CppCon, I can run a new installation, and it will pick up that it has a new setup for these things because we track the files that it used to change, and then it will just rebuild in like a few seconds. It will have done a full setup again because everything is still cached, and you don't need to have like an actual non-incremental build like you would have with a normal Conda workflow. What can I show you more about this? Oh yeah, right. So again, the CI does not look different at all. So from this point on, we will have exactly the same thing. Pixi will set up the whole environment, will do the build for you, and will actually do the installation. And then you can still run your tasks like you would do in your terminal locally. And it will actually show you that it is CppCon instead of the hello world example that it was initially was. Yeah, let's go back to the presentation. So what was great about the work that we did next to Pixi is Rattler build. So we're in our company improving more than just the experience of installing. We're also trying to improve the actual experience of building packages. One of the biggest problems that was there was that Conda build was just very slow. So as you can see, the thing that we built, Rattler build, is not shaving off like compile time. Like for instance, for Pixi, it's still a Rust build that we need to do. It can still take a few minutes to get that done. But all the boilerplate around that has been speed up tremendously, making actual building these packages a lot more fun again. And this data is coming directly out of the build forum on Conda-forge. So these builds are really, really speeding up since we've released this. Also, the recipe format that you need for building these packages is now YAML instead of YAML plus some extra logic through comments. And that actually will give you a lot of red squiggly lines if you try to read it. This is not the case anymore. And I really needed to put in rattler.build because I just think this URL is just amazing. Let's share that for more information. So if you're a developer and you're like, okay, why should I use Pixi? Let me recap, because I hopefully showed you some cool use cases. But the main focus is I want everyone to have a reproducible developer workflow. So something that you can try out locally, give to your friend, give to your colleague, give to your CI, and they will have the same exact experience as you had locally. Also that you will not be starting to break other projects on your machine. So if you have a pip installed environment, if you have an opt installed environment, this is all global. So then as soon as you update some packages, it might actually break another project that you are working on. Switching between projects by switching between terminals is a great experience that I would recommend for everyone. then the ability to set up CI in like seconds instead of dealing with, oh, how should I do this in a Docker image? How should I do this in this specific CI setup that I'm requiring? Doing the exact same thing as you're doing local is the actual dream for CI, in my opinion. Then these packages that I just showed you, you can easily just run Pixi build on them. And then you will actually get a Pixi package, or sorry, a Conda package out of that. And that is just reproducible, distributable through your normal channel experience. And last but not least, this is all cross-platform. And we really want to take care of the problems that you are experiencing with making sure that it works on all the machines, so you can actually have fun with the development of these applications. You can try it out today. If you scan the QR, you will go to our documentation page. If you have your laptop open, you can run this call command and you can try it immediately. It's a single binary. Package manager shouldn't need a package manager, in my opinion. Have fun with it. I hope you thought it was cool. If there's any questions, then let me know. Thank you.
Hey, thanks for the talk. That was great. You said you have like 30,000 packages?
Yes.
I was wondering if you have anything for the ROS ecosystem?
Oh, that is an amazing question because I have it on my card. I am a big robotics fan, and that was what I came out of. Yes, there is a robotics channel, actually. It's called RoboStack. It has a different philosophy as Conda-forge, where Conda-forge will build all the packages in their own repositories and then push them to a general repository. RoboStack will do it in like a monorepo style, where there's an automated logic to go from the ROS distros directly to the Conda recipes, build that for you and push it there. But just add Conda-forge and RoboStack, and then you will have the ability to install ROS packages. Yeah, that works.
Hi, thanks for the talk. You mentioned how Pixi can read PyProject TOML files. Is there any active development on reading cargo TOML files the same way?
I didn't have it in my example, but if you use Pixi build, these build backends can read whatever you develop them to read. So our Rust backend, because these backends, we currently have CMake, Python, but also Rust, Mojo, more of these things, they will be able to read that. So in the cargo example, you will not have to define a name, a version, all of that stuff will be read out of the cargo tunnel directly.
That's awesome. Thank you.
Thank you.
Hi again. Great talk. I had two questions and a comment. The comment was that regrettably locked environments are not necessarily reproducible because sometimes packages are removed and then the environments are broken, but that has nothing to do with the talk. My first question was, why was the address of Conda-forge different? Why did you go through prefix deb?
So for everyone
the
who didn't
standard
pick that up,
Conda-forge, yeah.
I used the prefix mirror mainly because I...
Also, it's just a mirror.
It's just a mirror.
Okay.
I use it in this case, not to just like show that we're also having that option, but it's actually a lot faster. So where you're using the normal Conda-forge from Anaconda, you will download a multi-megabyte file if the repository updates. We actually implemented a new way of downloading these files, so we can download shards. So in this case, if only Python updated, I only need to download like a few small kilobytes of change instead of a huge amount of data. And for demos, it's just so much faster that I need.
And is this something that other firms or people can reproduce locally? Their own channels, like that run in the same way?
Yes, it supports completely the same logic as a Conda.
And then my second question was, did I understand correctly that there's a separation between a workflow and environments in that workflow? So in the sense, can I activate an environment from anywhere, or do I have to be in the directory for that workflow where the .pixi is?
So the quick answer is yes, you have to be here in the folder, but you can, of course, define a manifest path. So just give it a path to the root of your project. And we actually have an issue open that I wrote a few weeks back to give the same workflow as Conda, where there's like a global registry of the names.
Right. Thanks.
Thank you. Okay. If that's it, sorry. I can come outside if you have more questions. Thank you, guys.